Hello, my name is Peter Amstutz. Today, I want to talk about building a federated data commons using the Arvados open source platform. Data commons is an emerging concept, but at its core it is about facilitating the use and reuse of data by making it accessible to researchers to use in their own experiments and analysis. In the biomedical space, data sets are often very large or have patient privacy concerns, so it is desirable to be able to analyze data directly on the Data Commons platform, unencumbered by the need for privileged cooperation by the data provider. This means the Data Commons platform needs to combine access to data, access to compute infrastructure, and the ability to run software on that infrastructure that supports the desired analysis. We suggest that building data commons on modular, community-driven, open, and standards-based platforms also facilitates interoperability and the sharing of analysis and results, which are essential benefits of the data commons concept. The following 9 technical requirements have been proposed for data commons. I won't read them all here, but we will refer back to this list. Arvados is an open source platform for managing, processing, and sharing genomic and other large scientific and biomedical data. It is commercially supported open source with an active user and developer community. Arvados can be deployed to various cloud providers as well as on-premise HPC clusters. With Arvados, it is possible to access and use data located on multiple clusters that may be running in different locations, environments, or organizations. Sharing raw datasets can be daunting when the data produced by instruments such as sequencers and microscopes can produce hundreds of gigabytes of data in a single run. Arvados works at petabyte scale and can manage thousands of cores to enable analysis of that big data. Arvados also keeps a complete record of everything done on the system, so it can determine what was done, confirm or reproduce results, track the origin of data, and be able to verify that a dataset has not been modified or have a history of changes when it has been. Let's start with a demo of Arvados in action. The Personal Genome Project, or PGP, is a network of projects where participants have released their genetic data under consent that allows for unrestricted scientific research. The Arvados project originated from and serves as the technical foundation for the founding PGP project, Harvard PGP. In this demo, I will show how Arvados could be used to build a data commons for PGP. In this demo, we have 2 Arvados clusters connected in a federation. The Curie data cluster has data from the Harvard PGP. The Arvados playground has data from the United Kingdom PGP. The data is stored as a set of collections in an Arvados project. Each collection stores 1 or more files that were contributed by a PGP participant. The collection has a UUID and a portable data hash and a set of property metadata such as a participant ID, study, source, and data type. We can search for other collections using these properties. For example, we can search for all 23andMe data by going to the search bar and selecting Advanced Search, then searching for the data type 23andMe. This will perform a federated search on both Arvados clusters and return results from both PGP projects. If I click on the first result, we leave the Curie data cluster and are now viewing the collection on the Arvados playground where the data is hosted. We have several different ways to access the data. This dialog box gives connection information for a network folder or an emulated S3 bucket. Going back to the Curie data cluster, we want to collect all the data in this project that matches the data type 23andMe in order to do our analysis. We can use a short Python script to access the API and copy all of the files into a single collection. This collection will be the input to a workflow that will run an analysis over all the files. Let's run the script. This is pretty fast because none of the actual data is being copied. Our new collection just has a reference to the existing data. This also means it doesn't use any additional storage space. However, if we changed one of the files in our collection, it would make a copy of the file with our changes. The original collection contents would not be affected. Here's the new collection with the collected 23andMe data. It has a new UUID and it has 926 files. We're going to use this as an input to our demo workflow. So we'll copy the portable data hash that is referenced this collection. We're going to use this portable data hash in the input parameter file for the workflow. We're going to run a workflow to estimate ancestry of each of these PGP participants based on their 23andMe data. For our ancestry estimate, we use Pickrell's open source ancestry tool that wraps around Structure, a program for population analysis developed by Pritchard et al., and a set of reference data. We'll run the workflow at the command line. The workflow is written in Common Workflow Language, which is a standard for writing workflows that are portable across a variety of platforms, including Arvados. This is our CWL ancestry workflow. This is the input parameter file. We need to know the project UUID where the output should go. So we'll go back to Workbench and copy the UUID of the project. And now we'll paste it into the command line. And we just need to provide the name of the CWL file and the input parameter file. Now Arvados CWL runner is submitting the workflow run to Arvados. We can go back to Workbench, where the workflow now shows up, and we use Workbench to monitor the progress. We ran this workflow on the Harvard PGP data on the Curie data cluster. So now we want to run it on the United Kingdom PGP data on the Arvados playground. This dialog box gives us the information we need to connect to the Arvados playground from the command line. We'll copy and paste it into the command line to set up our environment. We're going to run the same Python script to collect our files, and the only thing we need to change is the UUID of the project we're going to search to reflect that we're searching on a different cluster. Now we rerun the script, and this is going to produce a collection that has all of the United Kingdom PGP data. Now we're going to we copy the portable data hash, and we're going to run the same CWL workflow to do ancestry analysis that we used before. We just need to update the portable data hash of the input data set. Because our collections are referenced by portable data hash, we don't have to change the references to the reference data at all. We only had to change the primary input. We can even use the exact same command line, and almost the same command line. The only thing we need to change is the project where the output of the workflow is going to be stored. And that's all we need to do to submit a workflow to run the same workflow on different data on a different cluster. Let's talk about some of the Arvados Data Commons features we saw in the demo. Data Commons Technical Requirement 1 is data identification using persistent digital IDs. The Arvados storage system is called Keep. We saw how Keep organizes sets of files into a collection which has a human-readable name, a database UUID, and an immutable identifier based on the data content called a portable data hash. The portable data hash is extremely useful because in addition to being immutable, it is location independent. As we saw in the demo, by using portable data hashes, none of the workflow reference inputs needed to be changed to run the workflow on a different cluster. They just naturally refer to identical copies of data on the new cluster. Data Commons Technical Requirement 3 is services for assigning and accessing metadata for digital objects. We saw how Arvados makes it possible to search and query user metadata. Data Commons Technical Requirement 9 is storage resources for cloud-based analysis of data. The clusters used in this demo run on Amazon Web Services and thus are able to store huge amounts of data using S3 buckets. Data Commons Technical Requirement 7 is workflow services for executing bioinformatics pipelines for data analysis and harmonization. We saw how you can run C2BL workflows on Arvados. Data Commons Technical Requirement 8 is ability to process authorized computations from systems and return results. We saw how the workflow can be submitted at the command line, which is suitable for integration with other systems, as well as submitting through an API or through the web workbench. Data Commons Technical Requirement 9 is compute resources for cloud-based analysis of data. Requests to run a compute job are submitted through the API. Crunch can easily satisfy the compute request by using the cloud provider's API to request a new compute instance on demand, running the job, and then shutting down the compute instance when it is no longer needed. This allows for scaling up to support huge computations when needed and scaling down to minimize costs. For day-to-day use, Arvados offers a web workbench application and command line tools, which we saw in the demo. Data Commons Technical Requirement 2 is data and data model exposed through an API. As we saw in the demo, Arvados can be accessed programmatically through an API. Arvados offers software development kits for several different languages, currently Python, Go, R, Ruby, and Java. SDKs make it easy to access the underlying REST API as well as direct access to data store and Keep. In addition, software can access files and Keep through WebDAV and S3 compatible APIs. Because biomedical data is subject to privacy regulation, Data Commons Technical Requirement 5, Security and Compliance Services to support controlled access data, is essential. All access to Arvados API endpoints require the client to present an access token that identifies the user. All traffic is encrypted by default using TLS, and Arvados can be easily configured for data to be encrypted at rest. Use of the system is logged to support audits. Data Commons Technical Requirement 4 is interoperating with third-party authentication. Authorization services from trusted platforms. Arvados supports various single sign-on systems, including Lightweight Directory Access Protocol or LDAP, OpenID Connect, and Google accounts. All data uploaded to Arvados is private by default. Users choose what to share, who to share it with, and at what level of access it is shared. You can also configure Arvados so that users have the ability to run analysis on datasets, but not download the data directly. Data Commons Technical Requirement 6 is interoperability with other trusted resources with similar security and compliance. We saw how Arvados clusters are able to communicate with other clusters in a federation. In the demo, we were able to go back and forth between the two clusters seamlessly. This is possible because Arvados supports the use of a single identity and credentials across federated clusters. We saw search and data access across the clusters. Federation enables interoperability between different regions or even organizations. The administrator chooses which clusters to federate with. Federation facilitates the data commons by making it possible for data to be shared widely among users in an organization or between organizations while still having controlled, audited access. Thank you very much for your time, and we now have a few minutes for questions.